So our speaker today is Dr. Helen Fraser from the Open University. Dr. Fraser is a lab astrochemist, so that means doing experiments in a laboratory to work out what chemistry is going on in space. She did a PhD at the University of Cambridge. She's had jobs in Nottingham, San Francisco, Leiden and Glasgow, and now works at the Open University in Milton Keynes. She's a member of the RAS Council and has a role in our 200-year celebrations, which are coming up in a few years' time. So without further ado, I'd like to welcome Dr. Fraser to give you a talk on the cosmic chemical cauldron. Thank you.
So, good afternoon. I've been given very strict instructions to try and stand behind the lectern, and I find that a big barrier. So, if you see me going too far, it's like a Punch and Judy show. If you see me going too far, because they're videoing for all the people who can't be here today, just shout at me that I need to wander back. But I'm really sorry. I feel like I've got this slight barrier in front of me. Okay, it's really lovely to see all of you here, and glad that so many of you want to know all about what kind of chemistry happens in space. You probably don't often get to talk about chemistry at an astronomy meeting. But really, as astrochemists, we're motivated by a lot of things. We're motivated by the fact that our molecules in space, and we really want to know how did they get there, why are they there, what role do they play, and one of the key things about the role they play is the potential they have to give us the ingredients, the right mix that eventually can lead to the origins of life. So I wanted to start today by saying what is life and what is needed for life? Because I think they're quite important questions to challenge in our own mind as we start. So, what does life look like? Look around the room. That's one kind of life. However, here's another kind of life, and I do have to point out, this is me. And that's an oceanic whitetip, in case you're not sure. One of the 4 most dangerous kinds of shark in the world, and I'm still here, so it's really not that dangerous when you're under the water. Nonetheless, if we look around our own planet, and this is just a very, very small selection, life has huge diversity. And here I've pretty much put a lot of animal life. We also have plant life, we have bacteria, we have fungi. We have many different kinds of origins of different kinds of life. So when we're thinking about life in the universe, we are thinking on a very broad spectrum. But in actual fact, life, if we find it anywhere else in the universe, except the one statistical case where we know it definitely does exist, is probably not going to be very complex. It's probably going to be a very simple single-celled organism, much like an amoeba. But even getting to a single-celled organism, much like an amoeba, is a very complex process. And the question is, how does that happen? So, I need to point it that way. This is probably not what we're going to find and talk about today. Okay, what is needed for life? We also think about what's needed for our own life. We need to breathe oxygen. That's pretty important to us. We need water. And we need energy source. You know, normally we eat food. Hopefully some of you had lunch, or maybe you're going for lunch afterwards. However, in actual fact, only 2 of these are absolutely vital for life to emerge and evolve. And that is an energy source and water. And sometimes an energy source can be something you may not expect. It could be geothermal energy or energy generated by volcanic activity, wind energy, it could be solar energy, it could be many different forms in which you have some kind of energy input to a system. And water, of course, comes also in many forms. To us, it's really important in its liquid form. Actually, it's equally as important to us in our lives that it can actually be in a gaseous form and also a solid form, because those 2 things actually help the ecosystem for our planet to really work effectively. Nonetheless, in actual fact, all we really need for life to evolve and exist is those 2 things, energy and a water source. They're very important things we need to look for. So I want to take you on the journey that's involved with the astronomy that really goes right back to the start and lets us think about where do these things come from and how do we potentially put those ingredients on a planet for life to evolve. So I want to take you right back to the formation of stars and planets. And this is the star formation cycle. Some of you may be aware that the universe is a great recycling project. Does anyone know what generation of star our sun currently is? A third, fantastic. Whoever said that, win a prize. Excellent. It's really good news. Those of you who didn't know, it doesn't matter. It's a 3rd generation star. That means we've had 2 cycles of star formation before our own sun came into existence. That's pretty important as far as we're concerned as chemists, because every time we go through a star formation cycle, we're more likely to enrich what we call heavy elements. All the elements that aren't very light elements are much more likely to be produced as we go through star formation cycles. And that's pretty important because those tiny, heavy elements become very important for biological processes and for chemical processes. Now, I want to talk to you for a few minutes just about this picture, and I'm going to step this way a little bit so that I can see what you can see. Obviously, because it's a star formation cycle, we can pretty much start where we like in the diagram, but I tend to like to start here. Now, this is an image of a peanut. No, it's not. But it looks a bit peanut-shaped, doesn't it? It's actually a visible image taken with a visible telescope of the sky, and what you can see is a kind of peanut shape where it seems that there are no stars. The ancient Egyptians used to think that this is where holes were ripped in the sky, and actually that there were no stars in these regions. It's not true. What this is it's a giant molecular cloud. It's a cloud of gas and dust. And what the dust is doing is scattering the starlight. It's actually, taking the stars that are behind there, the light is travelling towards us, light is being scattered by the dust, and then we can no longer see the light, and therefore it appears that there are no stars. There are stars behind this cloud, we just can't see them. You have a very similar process if you want to go home. Please be careful. Take a candle and light it and make a slightly smoky candle, and then try looking through, and you'll see where the smoke from the candle is, you can't see through. Please don't put your head too close or burn your eyelashes. But this is basically the same kind of process. These molecular clouds that are full of gas and dust are really the stellar nurseries, the place where stars are born. They're also the place where we see the most chemistry occurring in space. They're really full, packed to the brim of molecules. So we know that molecules are synonymous with star formation. Chemistry is synonymous with star formation. And that's what makes, especially in the current era, chemists so vital to astronomy. Now, for reasons we don't fully understand, but there are some mathematical equations, I figured you might be grateful if I spared you those this afternoon. But for various reasons, what these clouds start doing is collapsing under their own gravity. And regions of the cloud, small clumps of the cloud, collapse under their own gravity to start forming new stars. And this also is a very famous image from the HST, from the Pillars of Creation, it's called. And this is a dusty sort of filament which is being lit by nearby stars. And if I put the laser pointer on one of these tiny little pinnacles on here, then the diameter of my laser pointer spot is roughly the size of a new solar system that's forming in this enormous object. Suddenly you get a sense of scale. And what's actually happening in this object is in lots of different regions, these dense cores are collapsing. And at the centre of these dense cores, new or baby stars are forming. We call them protostars. And then a very interesting process happens. This is a visible image of the Orion Nebula. And if we look at certain points in this image, we can actually see some black smudges. Yet again, this is exactly the same thing we saw here. It's very dense dust scattering the light so that we can't see it. Now, they seem to have lots of different shapes, but this is simply a sort of matter of the geometry between the object we're looking at and us on the Earth. Basically, what's happening is a baby star is forming at the centre of a cloud of gas and dust. And due to conservation of angular momentum, due to the physics of the process, essentially what we do is we flatten this material into a disk of gas and dust that's circulating around this newly forming star. And it's in this disk of gas and dust, through accretion processes, that planet formation occurs. And so eventually, when planet formation occurs, we have the potential to form life. I'll explain why that is in a little while. And then we get to a mature solar system. Now, I'm now going to throw away all the rest of astronomy, because stars live and they die. That's the whole of everything you're probably normally used to listening to. When they die, they do interesting things, but I'm not interested in any of that. And all of that material comes back into the interstellar medium and starts the process again. Even in modern astronomy, we don't fully understand how to form these molecular clouds. And even in modern astronomy, we don't fully understand the collapse. We don't understand the planet building process. And the interesting thing is, all the way from here through to here, we have chemistry going on. And so chemistry potentially gives us the handle to understand this side of the process. Now, I've used a couple of words, and I might use these words as I go through my talk. They're slightly technical words, so I thought I would take a quick 10 seconds to say, oh, if I use these technical words, you can roughly remember the picture. So these things, before they collapse, these molecular clouds, can also be called prestellar cores. Then when they're collapsing, they're called collapsing cores. And then when they're actually forming new stars, they're called young stellar objects, YSOs, young stellar objects. Now, all of this material is known as the interstellar medium. That's the medium from which the stars form. It's 99% by mass gas, which is predominantly hydrogen, hydrogen gas, molecular hydrogen gas, and helium. And 1% by mass dust, which contains all of these different chemicals, if you can remember a long way back into what you did in chemistry. Okay. How do we know about all of these things? Well, the first thing we have to do is we have to think about, obviously we can't go and look at star-forming regions in the visible part of the spectrum. It's completely obscured by dust. So we have to go and look in different parts of the electromagnetic spectrum. Now, some of you may be familiar with the electromagnetic spectrum, some of you less so. All of you are using this tiny part of the electromagnetic spectrum like right now, the visible part of the electromagnetic spectrum. And if you go out in the sunshine, you sometimes get exposed to this part of the spectrum. If you break your leg, this part. Pardon me. When you go home and you listen to the radio, you expose yourself to this part. But in each part of the electromagnetic spectrum, in astronomy, we call it multi-wavelength astronomy, we see objects very differently. Now, this whole concept that now we can look across the whole region of the electromagnetic spectrum and see things, the same object in different light, is a very, very important concept in modern astronomy. As you can see, this is a galactic picture. You can see that in every part of the electromagnetic spectrum, you get a completely different picture of what was going on. If you had X-ray vision, like Superman, the universe would look incredibly different to the night sky that you see with your human evolved visual seeing eyes. So which kind of detector you're using actually gives you a very different view of the universe. And this is very important for us in astrochemistry because the most important part of the universe for us in astrochemistry are these three areas: the radio, the millimeter, and the infrared. Let me show you why. Why is the infrared so important? Let's watch what happens. Anyone know this constellation? Oh, good. That's excellent. Orion, excellent. So this is what Orion looks like. Imagine if you had infrared eyes or an infrared camera. This is what Orion looks like. Let me just go back and forwards just a second. So there's the visible image. You probably don't see it this beautifully from central London. But this is what it looks like actually in the infrared. And interestingly, this is the Orion Nebula. This is the closest region of star formation to Earth. This is one of the regions where the ancient Egyptians also thought that their pharaohs were reborn as stars in the sky. So they weren't completely wrong. They picked a star-forming region. They did quite well. And obviously, what we can see here is really bright heat radiation being emitted in a star-forming region. This is all the dust being warmed up by the baby star at the centre, emitting lots of radiation. So suddenly, the dust becomes our friend and not our foe. And that's one of the reasons why, when we're looking at star formation, we're interested in looking in infrared and longer wavelength regions. Oh, excuse me. So slightly earlier I said that these regions of star formation, these molecular clouds, these prestellar cores that then collapse and form YSOs, I used the word stellar nursery and I used the word molecular cauldron, those two things together. How can we be certain that we know about these things? Well, this is an image which came from a few years ago from the Spitzer Space Telescope. It's called the Mountains of Creation because it was named by Americans after their pillars of creation, which came with HST. And what you're really seeing here is a false colour image, but what you're seeing is what's in red is really an image of where all the dust is. And you can see again, there are regions of dust with bright infrared objects inside them, which is where we have star formation happening. Now, it's pretty important to understand what kind of conditions we have in interstellar space. The temperature is about 10 degrees Kelvin. That's minus 263 degrees centigrade. Definitely a temperature at which you would get your winter fuel allowance, but they don't pay it to interstellar molecules. On the other hand, the pressure, we call these densities and pressures high pressures in astronomy, but the pressure is 18 orders of magnitude less than the pressure in this room. That means if you put a 0 and you put a full stop and you put 17 zeros and then you put a 1 at the end of it, that's the number we're talking about, because not everybody might like writing it mathematically like this, so that's the same thing. Basically, the pressure is incredibly low. How many of you know what an oxocube looks like? Pop your hand in the air if you know. Yeah, excellent. We're going to be interactive today. Yeah, no sleeping. So if you imagine an oxocube in this room, if I took an oxocube of volume and I worked out roughly how many molecules, there would be 10 to the power 24. So 1 with 24 zeros after it, molecules packed into, or atoms or molecules packed into an oxocube space. In space, there could be between 1 and a few thousand molecules in that oxocube space. And we call that dense space. So you can see that we're in very different conditions to those on the Earth. Okay. So let me change tack a little bit and sort of say then, if we're in those conditions, how on earth does chemistry happen in astronomy? Because chemistry requires for one thing to meet another thing and collide and do some reaction. And I'm just now going to get you for one moment to actually participate. So if you can, if you're able, I'd like you all to stand up, please. Okay, what I would like you to do very quickly, just turn to the person to your left, to your right, in front of you, behind you, say hello. Okay, thank you. I'm going to pick on Keith. Keith is going to stay standing up. The rest of you may sit down. Did anybody not find somebody to say hello to? Good. So you all had someone to say hello to. You've all met a new friend suddenly. Now, Keith is like a molecule in space. Now, I don't exist, and Keith has to find someone to say hello to. Poor Keith can find nobody standing up to say hello to. And that's what it's like for the molecules in space. You can sit down now. Thank you very much. That's what it's like for the molecules in space. They don't find it easy, like the molecules in this room, like the people in this room, to find someone to go and bump into and form a new molecule with. Unfortunately, they're all by themselves. And so this makes it very difficult to understand how the chemistry might happen in space. Anyone know what this is? Oh, good. Fantastic. Good. So periodic table. Now, if we think back to, I don't know, chemistry at school or something like this, I don't think I'm telling you any surprises that on this side of the periodic table are metals, on this side are non-metals, and somewhere in the middle are transition metals. You might have heard those words roughly before. Great. Okay, and there's one pretty important metal which is here, which is iron. It has a special magic number in its nucleus, and if you're an expert in nuclear physics or nuclear synthesis, you know that through the processes of nuclear synthesis, we can go all the way through the molecule, the elements quite easily up to iron. After iron, it gets much more complicated to make all these heavier elements, and in actual fact, after we get to uranium, all of these things after this are not naturally occurring. They're very highly radioactive. But nonetheless, we have all of these elements. We know they exist on our planet. We know they were formed in the stars. We know that as we go through different formation cycles, we go to heavier elements.
Sorry to interrupt. Could you confirm that all that basically came from hydrogen initially?
No, it doesn't all come from hydrogen initially. No, it's a very complicated process. Not true. You could talk to me afterwards, but we're going to come into that today. No, it's a very good question. But I could give another whole talk on it, but I shan't. Otherwise, you'll all be here till 3 o'clock. Tummies are rumbling. Okay, this is the astronomer's periodic table. Okay? Now, the astronomer's periodic table has the boxes of the elements roughly equated to the size of the abundance or the amount of the molecule that we find in the universe, the atom that we find in the universe. You'll notice that the majority of the 92 known naturally occurring elements appear to be missing. They're not missing, they're not found in the universe. I just don't have a pixel size small enough to put them on this plot. So you have to imagine they're there, but you can't see them. The other interesting thing, which I spent years scratching my head over when I moved from chemistry to astronomy, was how astronomers define metals and non-metals. I don't know about you, but there was a list of 7 rules when I was at school about what a metal was. You know, it was shiny and could be polished. It had, you know, an atom in a sea of electrons. I don't remember all 7 rules. There were some very clear rules, okay? If you talk to a physicist, if you put this thing under very high pressure, you can make it behave like a metal. So hydrogen can have a metallic-like state. However, astronomers throw all of this information out the window. The basic way that we define whether we've got an element that's a non-metal or a metal is basically, was it a byproduct of the Big Bang? Was it something that came just after the Big Bang? Or is it something that is a byproduct of some kind of nuclear process, nucleosynthesis in a star? As a consequence, hydrogen and helium, made in the Big Bang, just afterwards, and everything else made when stars start doing nucleosynthesis and nuclear burning. What you will notice is that the next most abundant elements are carbon, nitrogen, oxygen. Combine together carbon, nitrogen, oxygen, hydrogen, you have a huge amount of organic chemistry going on, and that pretty much accounts for almost all of biology. Never mind the small things like phosphorus or calcium or magnesium or anything else. That's pretty much what we need. So it's very interesting that these are the ingredients we've got available to do our chemistry with. In actual fact, so far we've found over 240 different chemicals in space, almost all of them in interstellar space, a few exotic ones around stars themselves, actually over 50 and counting now molecules in extragalactic space, some of them as far as a redshift of 7. We've even found water at a redshift of 6. So very far back into the early formation of galaxies, we're pretty certain that all of this chemistry is actually occurring. Some of them are molecules you'll have heard of before: carbon monoxide, hydrogen gas, carbon dioxide, water, methanol, and ethanol. And I should say that as professional astrochemists and astronomers, we have an incredible alcohol problem. Not the kind you might expect that at conferences we can't put it down, although that does sometimes happen. But actually, methanol and ethanol are 2 molecules which we know are formed through chemistries that occur in the star formation process. So we know that we need stars to be forming in our models and our understanding of the chemistry in order for these molecules to form. However, if we go and look carefully in observations, what we see is huge methanol and ethanol masers beaming out of the sky in radio frequencies long before star formation happens. In actual fact, the presence of these alcoholic lasers is a wonderful indicator that star formation is about to happen. So we have a real chicken and egg situation in that one way we understand how a chemistry should happen, and in the other case, it clearly isn't quite happening that way. I can't give you the solution. It is known as the astrochemical alcohol problem. Nonetheless, the interstellar medium is very rich in molecules. Even from the simplest molecule, dihydrogen, molecular hydrogen gas, to those potentially necessary for the formation of life. We've found amino acids in meteoritic samples. We can find very complex things, Buckminster fullerene type buckyballs, C60, we've seen those in space. We see complex polyaromatic hydrocarbons. They're the kind of thing out on Piccadilly you definitely don't want to be breathing in, highly carcinogenic, but they pervade space. But we see simple molecules, formic acid, acetonitrile, ethane, all sorts of different molecules in space. So despite the fact we've got Keith stood all on his own not finding any mates, and we're at very low temperature, and a little OXO cube has only got a few 1 to 1,000 molecules in it, chemistry is definitely happening. So you might say to me, well, this is all very nice, you've told me the story, but can you prove to me that the interstellar molecules are there? How do you prove to me that the interstellar molecules are there? Then we need to know, how do we observe the interstellar molecules? We're astronomers, we like to go observing. So what we actually do is we don't use a technique called imaging, but we use a technique called spectroscopy. In other words, the interaction of light with matter. And if you decide that you want to go afterwards to the library, I believe today the RAS librarian has put some of the books out that are in the library collection that are associated and related to spectroscopy, so that you can see what's in the collection. Okay, so we go to telescopes. These may be ground-based telescopes, they may be telescopes based in aeroplanes, they may be space telescopes. And basically we work either in the infrared or we work in the millimetre, sub-millimetre or radio wave, and we point our telescope towards a star-forming region. Now, we can observe lots of different things in the star-forming region. If we want to observe the solid material, like the dust, we usually observe that in absorption, which is what is illustrated here. There'll be some kind of absorption spectrum on the black body continuum curve of the object we're looking at. That might be a star embedded, a baby star embedded inside, or it might be a star that's not at all associated with the star-forming region, but happens in our sort of parallax to lie behind it, and we use it as a source of light to probe what's lying in the line of sight. And basically what we get out is a plot of how there's a change in absorbance of the light, or actually in the gas phase emission of the light, against the wavelength of the light we're looking at. Now that can be a bit confusing, so I want to come back to my electromagnetic spectrum again. As a chemist, I know that across the electromagnetic spectrum, different interactions occur with atoms and molecules at different frequencies. And the ones that are most important for what we're interested in are these ones here. Molecular vibration, which occurs in the microwave, the infrared, and molecular rotation, which occurs in the microwave. So here they are, just here. These are the really important ones. And this happens to be, very fortuitously, as I've just started saying, the region of the spectrum where we happen to be looking through the dust and being able to see all this interesting process going on. Now, I'm going to get to an interactive point again. I wonder if I can have 3 volunteers, otherwise I shall pick 3. Are there 3 of you willing to volunteer to come up on stage and help me out for a minute? Keith is coming, Pamela's coming. Pamela's coming. Can I have one more person? Great, brilliant, come on up. Can we give them a round of applause for being really great and volunteering? Okay, I'm just going to say to the camera there right now, I'm very sorry, but I have to walk for this bit, so if you're watching on the web, you might not entirely see. Can you guys each find a bit of space at the front? I suggest one of you goes here, one here, and one there. Now, what these guys are going to be is they're going to be water molecules for me, okay? Now, water has H2O, so it has 2 hydrogens and 1 oxygen. If I do this for a minute, there we go, that helps. So it has an oxygen in the middle and 2 hydrogens, and it's a V kind of shape. Can you all make yourselves a V kind of shape? No? All of you? Yeah, that's it, great. 3 water molecules. Okay, Pamela, I'll give you the easy one, right? Pamela is going to show you how water molecule vibrates by going like this. Okay, brilliant. And what was your name? Hela. Hela is going to show us another way a water molecule can vibrate by going like this. Okay, keep going. It's good exercise. No, you're going to do the bend. Okay, so these are the ways, in which a water molecule can vibrate. Now, there's one more little tricky step, guys. In actual fact, when you excite a water molecule's vibrational modes, at the same time you excite its rotational modes. So very slowly on the spot while you're still vibrating, can you turn around? Keep going all the way around. These are my water molecules. Now let me come back to my diagram. Let's just give these guys a round of applause and sit them back down. Thank you very much. In actual fact, these modes are very specific to a molecule. We call them fingerprints. Every molecule, depending on how the atoms within it are bound together, has these very specific rotational and vibrational modes. In actual fact, there's a very complex physics behind it. I don't want to go into it. But the very simple thing to remember is if you have light of certain wavelengths interacting with these molecules, when the wavelength of light or the energy is sufficient to excite one of these modes to get it going in that particular way, then basically the molecule absorbs energy. So what happens is we see a loss of energy in the spectrum. And this is the symmetric stretch. This is the one where we were going like this. And the asymmetric stretch of water. And this one here was what Keith was doing. It was the bending mode of water. And they come at very specific wavelengths. So if when we look in space, we look at a spectrum, we do spectroscopy, if we see loss of radiation at certain specific wavelengths, then we can start to understand which molecules we have present in our interstellar cloud. That's how we can do it. Okay, and what this actually means, this is a very recent paper, it's in Science in 2014 in case you want to go and have a look. But now we have very modern telescopes. This is a picture of ALMA. This is the huge array, sub-millimeter array, which is in Chile. And really, we're calling this the decade of astrochemistry. With facilities like this, we're able to do unprecedented searches for new molecules and unprecedented searches of where molecules are in space. It's really becoming the tool to go to for all astronomers. Even extragalactic astronomers and cosmologists are starting to use molecules more and more. It's really exciting. And basically, this is a view towards just off the galactic centre, Sagittarius B2. This is a distance around 300 light years. And towards this object, these two molecules were detected. Now, why are these two molecules particularly interesting? Well, they're not particularly interesting. I'm not going to tell you which biological function they have. They don't. However, this is a very long chain molecule, and this is what we call a branched molecule. They're isomers. They have all the same number of atoms in them. They're the same type of molecule, but the atoms are arranged a different way. And the reason this appeared in Science is because this molecule is the very first branched organic molecule ever to be discovered in space. And it tells us something because the formation route to forming a molecule like this and this is very, very different. So it tells us something about the potential chemical mechanisms that can be occurring in space. We don't know the answer, but we do know they're there. And we can detect molecules like this.
Highly poisonous cyanide.
Yes, it is. Don't worry, we're not. It's in very low concentrations. Remember, you've only got you've not even got one of them in the little OXO cube. In actual fact, why is it so important? Actually, is even better demonstrated by this. If we use radio telescopes on the ground, we can detect a large number of molecules. This is a whole swathe of molecules which have been detected by radio astronomy. Now, you don't have to understand what all these molecules are, but what I want you to do is look at the pretty pictures. And what you notice is all of them are very long, well, except this one. We'll ignore this one, but all of the others are very long chain molecules. Yeah? There's a reason why this one's like this. It's the most stable, but they're all long chains. And the interesting thing about long chains is that they have what are called huge dipole moments. When these things are spinning round, if I spin round, if you think about me holding the remote, if you look for when I turn, when the remote goes past you, it looks very different every time I'm turning round. And that's, in essence, that's what we're trying to do in looking for molecules with large dipoles. We're looking for molecules where there's a huge difference in how it's interacting, if you like, with the radiation as it's spinning round. And it so happens that all of the physics tells us we're most sensitive to long chain molecules. Does that mean that space is only full of long chain molecules? Absolutely not. What it means is our detection methods are most sensitive to long chain molecules, and so they're the ones we happen to have found to date. Now, actually, the key to forming these very large chain molecules is not gas phase chemistry at all. It's not one person accidentally bumping into another, saying hello, holding hands and going off into the sunset. No. What it is it's actually that we need to force these molecules together. And one way to do that is to be on a surface. So we're going to do one more little thing. Can you all stand up again for a minute, please? I hope that you're all feeling quite cosy. If you can, what I'd like you to do is link arms with the person beside you. Okay, please be gentle with each other. Okay. Now, if you now try moving, okay, you're much more limited in the movement you can have than when you're not on your arm. Just try gently moving. Please don't go too far. Okay, if the one person at the end of the row walks too far, you'll all be falling over. Okay? Now you're all linked together like the atoms and molecules in a solid. They're very close together. Have a sit down. Give yourselves a round of applause for joining in. Basically, in a solid, what you basically find, or what you basically discover, is that, imagine now we've got a solid that's the size of an OXO cube again. In the gas phase, we had, say, 1 to 1,000, pick a number randomly, atoms or molecules in that volume. on a solid, on each surface, so now imagine the surface of your OXO cube, any face of the OXO cube, you've got around 10 with 15 zeros, or 1 with 15 zeros after it, molecules just on that surface. And then you've got all those other surfaces, you've got a huge number of molecules. So what happens in the solid state is that we bring a huge number of molecules into very close proximity, and therefore it's much easier for the molecules to react. So what does interstellar dust look like? Well, we've never got a piece of entirely interstellar dust. What we have had is we've had missions like Stardust, which have sort of flown vertically, not out of the solar system, but through the solar system, put out aerogels, captured bits of dust flying through our solar system that may be interstellar or interplanetary, and we can see these different dust particles. What you can see is sometimes they've collided together and sintered. They're very complex, they're porous, they're very strange. They're pretty small in size, just a few microns in size. Now, if you're not sure how big a micron is, you can pluck a hair out of your head, or the person sitting next to you, I don't mind which. And if you hold a hair up, okay, if you were to look at it end on, I don't know how easy it is to look at a hair end on, but typically most human hairs are roughly around 60 microns in diameter. So that gives you a sense, if you could divide it by 30, you're roughly at the diameter of one of these things. So that gives you a sense of what size that is. Now I've got a hair in my hand. Never mind. As you can see here, this is what's called an interplanetary dust particle. This is probably made up of very many small particles, all sintered together. And this is pretty much the dusty material that was doing all that scattering, making that peanut shape in Bernard B68 that meant we couldn't see the stars that were behind it. This is what's to blame. In actual fact, we can look at this in an even better way. I said to you at the beginning, and the numbers probably went right past you, that 99% by mass of the interstellar material was gas that was hydrogen and helium, and 1% was this dust. So here's now a representation of 99 and 1%. Okay? This dust is roughly half solid material, like I've just shown you, and about half is what we call interstellar ice. It's condensed molecular material. So I thought, oh, I've got to explain interstellar ice. I'll quickly put interstellar ice into Google, interstellar ice images. So I put interstellar ice images. This is what I got. Kind of helpful, but kind of unhelpful. This is not interstellar ice images. Okay. This is a pictorial vision of what an interstellar dust grain is. An interstellar dust grain is something which is between 100 nanometers and a micron in size, onto which, as these clouds are forming, these prestellar clouds are forming and condensing, atoms and molecules from the gas phase stick to the surfaces and react and do chemistry. The simplest molecule we form this way, the one molecule astronomers love to look at, molecular hydrogen, can only be explained, its presence in space can only be explained if surface chemistry is happening to generate the molecular hydrogen. The molecular hydrogen is generated with so much energy, for those who are bothered, 13.6 eV of excess energy, if that means anything to you. If not, ignore that number, that it pops back off the surface. However, if oxygen and hydrogen atoms in some combination interact together, they form water. Water only has an excess of 5.3 eV, and as a consequence, it sticks to the grain surface. It forms a layer of water ice on and around the grain. And this layer of water ice, water is the most dominant molecular material in stellar space, actually. So after molecular hydrogen, we have water. But it's practically all in the solid phase, in this phase where it's all closely packed together. In actual fact, as we get to denser and denser regions just before star formation happens, CO, which is one molecule, carbon monoxide, a molecule that is formed in the gas phase, also can freeze out or stick to these grain surfaces and form what we call CO ice. So we end up with this very pretty sort of layer of ice, a water layer and a CO layer. And then, as the star formation progresses and all these complex processes happen, these grains get very carefully processed by ultraviolet photons, by electrons, by cosmic rays, by heating. All sorts of things happen, and these generate a whole bunch of chemistry that goes on in these grains. Very complex chemistry that goes on. And eventually, the star gets so warm that just like on a cold morning, when you have a frost on your car, as the sun warms the car up, the water miraculously, without the help of de-icer or a scraper, evaporates and you have a clear windscreen again. You know, you just have to wait an extra hour or so. I don't have that luxury. I have to go to work. But that's what happens in space. These ices desorb. They sublimate. They go back into the gas phase. And as a consequence, they go back in the gas phase. And if we look in a star-forming region in the gas phase, what we see is not just these simple molecules, but all the complex molecules that were formed, all the really complicated molecules. So we have a way of forming those complex molecules. Now, this is what a spectrum of interstellar water ice looks like. So here we have a wavelength, and here we have, okay, flux, but absorption or whatever. This is this water ice band. This is the band that's related to the water doing this. And this here, this is the bending mode of the water. It's related to the water doing this. That's all we're doing. We're looking at exactly the same stuff. And so as a consequence, what we see is we can see lots of different species of these icy materials in space. I don't want to say anything more about this one, or this one. So I want to move on and just say then, how does this chemistry happen? You know, we've got all the ingredients. We know the molecules are there. We know we've got low temperature, low pressure. We know we could do the surface chemistry. In actual fact, there's two other things that we have to really consider before we can understand the chemistry. Oh no, more words. Thermodynamics, right? Do we have enough energy for the reactants to form products? And kinetics. We have lots of time, but can the reaction proceed? Now, these are lots of words and it's a bit annoying, so I like to explain this a different way. I'm sure you can all think back to when you were teenagers. Now, when you're a teenager and you really, really, really like someone, you like to go on a date with them. Actually, I don't think it really matters whether you're old or young, but teenager is a better example. It's away from all of our ages. And you really, 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 really like someone, okay? You have to do a bit of thermodynamics before you can ask them out on a date, right? You have to overcome a barrier. You have to overcome the barrier of approaching them and saying, please, will you go out for a drink with me or come for a coffee with me or whatever, yeah? There's a barrier to the reaction happening, yeah? It's the same thing with molecules. They have to overcome an energy barrier, right? Now, how about kinetics? How does kinetics fit into my analogy? Well, imagine there's you and your best mate, and you both really quite like the same person, yeah? Now, if you're smart, you probably ask before your best mate, at least when you're a teenager, works better, because usually at that stage, you know, whoever asks first wins, yeah? That's why it's better to be teenagers than older, because we make different choices when we're older. So there's the kinetics. Not only do we overcome the barrier, but we overcome the barrier faster than anything else overcoming the barrier. So we win the prize. We go on a date. Yeah, I can't tell you what happens afterwards, not part of this process. But that's basically the two things that are happening with these molecules. And as a consequence of looking at all of this, we see all of these complicated reactions. I just want to point out with this figure, complicated reactions occurring on surfaces and in the gas phase. And so what we're able to do as chemists through theoretical calculations, through laboratory experiments, is work out all of these things. Now, I need to finish off, but I'm going to finish off, hopefully, by taking us really back into how this leads us to the process of planet formation. We've formed our molecules. We can try and understand how we've got those molecules. How do we bring those back to the origins of life? So what I have here, hopefully, is a little movie that really summarizes what we've been doing so far. We have a protostar surrounded by a disk of gas and dust. And in this disk of gas and dust, there is some rocky material. As we zoom in, hopefully, on this rocky material, we see that it's forming these icy layers. The ices are forming. And when we've got very icy grains, they start sticking together and aggregating in this disk. They initiate the process of planet formation. And these grains stick together to form larger and larger bodies, which we call planetesimals. And eventually, these planetesimals join together to form planets, or at least in this animation, very topical, a cometary body, a cometary nucleus, which then travels towards the sun. And as it travels towards the sun, it starts outgassing all the excess material that's in it. So all of these atoms and molecules, all of this chemistry that we've seen going on these grains and in space and everything else, gets locked into these icy grains and then incorporated into the material that's building planets. Okay, I'm going to skip this bit. So I want to finish off by talking about how do we then get from this material to really the origins of life. We might produce complex molecules in space, but it is a very, very big jump from a complex molecule, which may even not be an amino acid, all the way to these things. Yeah, quite a lot has happened. Quite a lot of different things have happened. And it's not a simple process. Now, one of the things we do know is that we live in a solar system. Our solar system has some gas giants, and it has some rocky terrestrial planets. And it has a planet out here that may or may not be a planet. But these things are very common. This is what we find most of the time when we look for other planets in other solar systems, when we look for exoplanets. These things are probably the things that are most vital to actually forming or harbouring life. Maybe the moons of these things are more likely to harbour life than the planets themselves. In actual fact, we have over 2,000 confirmed planets. We have what we call some transiting objects, and we have 3,400 brown dwarfs. That means that while I've been speaking to you, we've made about 1 million new solar systems in the universe. While I've been talking to you, we've made 1 million new solar systems, or at least we can see that that has happened. As a consequence, statistically, it's probably very likely that somewhere in one of them, somehow, there's probably life. So where does that life come from? If Keith will give me 1 more minute, I think I can probably answer that question. Well, not answer it, but if I answered it, I'd have my Nobel Prize already, right? Yeah, it's a shame. Okay, so what I've talked about mostly today is simple molecules, very simple molecules. Obviously, if we want to get all the way through to life, there are actually 2 key paths we need to follow. I am not a biologist, so this is just a gloss over picture. So apologies to those of you with biological excellence in the audience. But nonetheless, we can probably quite easily form complex molecules and polymers from simple molecules. That's not a difficult thing to do, chemistry-wise. The difficult thing to do is to form specifically the molecule of life, the DNA. Not just the RNA, but the DNA. Yeah? Because RNA is not a very stable molecule. So some people think there might be an RNA world that occurs before a DNA world, but it's very difficult to do. We know that all life, as we know it, needs some kind of DNA somewhere along the line. Even more importantly, biology occurs predominantly in the liquid phase, almost exclusively in the liquid phase, not in the gas, not in the solid. And everything I've told you about in space is gas and solid. And actually, biology needs chemical differentiation. It needs a barrier. Yeah, it needs a barrier which is high and low concentration. It needs a process of osmosis where something can flow from one side of a barrier to another. It needs some kind of cell or protocell. And that is absolutely vital for the emergence of life to occur. And these steps are the 2 really difficult steps that we absolutely still can't fully understand to get to here. That's our big challenge. We know we've got these ingredients. We know we can deliver these ingredients to a planet. How we get to this bit is still a huge issue for debate. Okay. Finish up. What I want to say is that interstellar gas and dust is the stuff that all new stars and planets are made of. In actual fact, each and every one of you in the room, please go see Simon Cowell and audition for the X Factor or Britain's Got Talent, because all of you are made of star stuff. Every single atom in each of our bodies, everything we see around us, at some point it came from the stars. It was put together this particular way at this particular moment in time. It's very fascinating. And because it's so fascinating, it gives us a very exciting universe to explore, and to explore using chemistry. Thank you very much. Yeah, absolutely.
Okay, so thank you, Helen, for a fascinating talk. We do have about 10 minutes for questions. As has been mentioned a couple of times already, this is being filmed for the website, so please wait until the microphone comes over before asking your question. So, go in the middle there, start with.
I am a chemist, and chemistry is very often about electrons. Now, you mentioned cosmic rays, which are stripped of electrons, they're heavy lot of electrons in space as well, going everywhere, but not going through atmospheres, of course. Could you mention anything about electrons?
Yeah. Dare I, oh no, I deleted the slide, so I can't. Yes. There are a number of ways in which chemistry can happen. It can happen in atom-molecule reactions, thermally induced, UV-induced. Actually, electrons are very important in the chemistry. They're not unimportant at all. I've skipped over it a little bit. In the gas phase, they're fundamental. Actually, most of the gas phase processes involve ion-molecule reactions, ion-neutral reactions, radical-radical reactions. So there, the electron, the electronic state of the molecule is playing the absolutely vital fundamental role. Most of the reactions that occur that involve electrons in the gas phase occur through something called dissociative electron attachment. Now, there's a horrible set of big words. What it basically means is it means there's normally a molecule, an electron comes along, it attaches itself to the molecule, and actually, in actual fact, the molecule falls back apart again. And then the constituents of the molecule go away and react with something else. And almost all of the gas phase chemistry is driven by this ion and dissociative electron attachment chemistry, which means it's fundamentally involved in what the electrons are doing. So it's absolutely true that the electron chemistry is vital. In solid state, it's actually very interesting. When you have a cosmic ray, it's not necessarily always that the cosmic ray itself is generating lots of chemistry. Cosmic rays are highly energetic. While you're sitting here, there are cosmic rays passing through you. They are not completely altering your chemistry beyond recognition. They may be doing some radiation damage, but nothing you need to worry about. But they're not absolutely fundamentally changing you, not all suddenly becoming mush or zombies or something else. On the other hand, when you're in an interstellar cloud, the thing the cosmic ray is most likely to encounter is an H2 molecule. What that does is it promotes or excites the H2 molecule, generating a UV photon, generating some ultraviolet energy. And that ultraviolet energy is then more likely to interact with the dust grain and drive the chemistry. However, it is a huge debate in our field at the moment, which you come right to the crux of. I was just in a difficult place to go to a conference, Hawaii, 2 weeks ago. And there was a huge debate going on between all of us. There's a field of people that only believe in this, photochemistry-driven process. And there's a whole field of other people, another camp, who say, well, even if a cosmic ray just interacts with a grain once, what it will actually do is it flies through the grain, is generate a whole bunch of secondary low-energy electrons. And that low-energy electron chemistry is really fascinating and can do much more than a whole, lifetime of ultraviolet chemistry. And actually, it's probably very true that these electrons are driving a lot of chemistry. Although, unfortunately, if we look at our observational evidence, all our observational evidence for the solid-state chemistry shows is that we have, at least until the star is switched on and the disk exists, in all of the earlier stages, all of the chemistry is thermally driven and atom molecule driven in the solid state, which is very interesting why that is happening. We don't fully understand. When the star switches on, it's more complicated because we get this complex chemistry. So it's a fascinating question because I can talk about it forever. It's very perceptive. Thank you.
Over there.
Hello, you mentioned when you started that all you need for life is energy and water. But when you do any kind of course about astrobiology, it's drilled into you that you must have carbon. Are you kind of putting that to one side and suggesting that you don't really need carbon?
No, you're absolutely right. Sorry, I just assumed that having the carbon and the molecules to go with it was no, you're absolutely right. That's a very good point. Before this evening, I shall add that bit to my talk because it's a slide I deleted actually. Carbon plus all these things equals life. Yes, sorry. Very good point.
I understood that the precursors of biological molecules formed in the Earth's early atmosphere, Miller's experiment and that. But does this work suggest that they were already present in the primitive atmosphere?
Okay, very, very good question. So for those of you who don't know, URI Miller did an experiment back in the 50s, actually. It's known as the URI Miller Experiment, if you want to go and look it up, where they basically put all the potential molecular gases, the simple gases that could have been in the early atmosphere, into a chamber and made an electrical discharge and found out what other complex molecules they could make. And actually, if you have a bit of ammonia, water, CO, CO2, and you put a big electric bolt, lightning bolt through it that looks like lightning, you form lots of very complex molecules. The question is, I think, really, whether or not these complex molecules can form before and be delivered to the Earth. But also there's another part of your question, which is the URI Miller experiment assumes that the water, the CO, the CO2, the methane have already been delivered to the Earth. And actually, those two processes occur the same way. As you have these comets and lots of different bodies, in the early formation of the solar system at least, we know that we had what was called a late heavy bombardment period. You may have heard those words used before. What it basically means is as everything was stabilising in our solar neighbourhood, a lot of material, especially from the outer solar system, came crashing into the inner solar system. Luckily, we have Jupiter there mostly now to mop it up. At the time, the planets weren't all quite in the same place. And we have all of this cratering that we still see on the moon, but we don't see on the weathered Earth surface. And all of this bombardment basically would deposit material, would deposit tons of material from space on the Earth every single year, will deposit material on the Earth. And this deposited material will have all the ingredients, the simple atoms and molecules that might be necessary to emerge life. It's not necessarily true that the complexity of chemistry in space goes so far as to produce plenty of amino acids and the amino acids come to Earth on the back of a comet or a meteorite and then they evolve. No. It's a combination of things. And the URI Miller experiment sort of comes as the next step. Once you've got the planet, once you've got an environment where you can have liquid and gas and everything else, where did all the molecules in the atmosphere come from? They're not all formed just by the lightning fixation. Some of them are outgassed in this process of late heavy bombardment, which enriches the atmospheric environment. And that's why we need all those processes together. There's both an exogenous delivery and a process of actually the chemistry changing once you're on the planet's surface itself. No little green men on my ice grains in space, definitely not. Or amoebas.
Okay, I think we're going to have to leave it there because we've only got a couple of minutes left. There's a few announcements I have to make before we finish. So I'd just like to draw your attention to the fact that on the Friday the 20th of March, that's 10 days away, the UK's best solar eclipse since 1999 is occurring. It's going to be about 90% of the sun's surface will be covered as seen from London. There are various resources all about this, how to view it safely and so forth on the RAS website. And we've also joined together with a local astronomy group to run a viewing event on the Friday mornings. It runs from about 8 a.m. till 10 p.m. in Regent's Park at the Smokehouse, which is a little cafe in there. There should hopefully be some leaflets outside. The second one is that the next public lecture here will be on Tuesday the 14th of April, when Dr. Stuart Clark will talk about the unknown universe, which is not the most meaningful of titles, so I looked it up. He's talking about the Big Bang and the early universe. And there are also additional lectures before that for the friends of the RAS. If you could pick up a little leaflet with all the lists of the public lectures in there, there's a section on the back about how to become a friend of the RAS and come on to some of the extra lectures. But after that, thanks for your attention. Let's thank Helen again for a fascinating talk.
Thank you.